All right, lab report. Make sure you pay attention. I got to do a lot of instruction. Don't forget, you need your name. You need your name up in one of the corners. We've done this before. Everything that we already know, I'm going to go pretty quick, okay? Pretty fast. We don't do any other headings or titles. You're going to go name, then you're going to go Roman numeral 1, space, and the word introduction. Got it. You guys already know you need 1 to 2 paragraphs. This is formal writing, so no use, no contractions, no personal pronouns, unless, of course, it's referring to a person you're talking about in the paragraph. What are you going to introduce this time? What was the lab about? pH. You are going to introduce the topic of pH. Since we're going college level this time, I'm not giving any ideas. I want you to write an introduction about pH, but do not talk about what you did in the lab. Got it? You figure it out. Roman numeral 2. Whoa. Roman numeral 2. This is the materials section. That's the materials section. You guys know all of the rules. You got to have 2 columns. You got to have an indicator. If you use a table, make sure you get rid of the lines before you turn it in. Right-click, format, get the lines out of there. If you have an extra one, it goes on the left, not on the right. What should you list in the materials section? Let me point in the right direction. What should you list? The actual materials we use, which are still on the side lab. I will not take them down until we turn this in. See, the only thing that's not over there is milk because it would have spoiled. I had to clean the vials up. You know how to do materials. 3. This is the part you might hate a little bit. Procedure. Let's clean up our errors from the last one. Remember, it's step by miserable step. 1 step at a time. No double steps, no triple steps. 1 step at a time. And we do continuous numbering all the way down. No gaps, no spaces, no subtitles, no headings. You just roll. Now, I will help you here. You must include procedures, and I would ask in this order, but I wouldn't ding you if it wasn't. But you got to do procedure for your baseline testing. That's when you put 4 pieces of pH paper on a paper towel and you tested each of the 4 samples to make sure you knew what the pH was before we started. Does everybody recall what I'm talking about? Then you need to do lemon juice and milk plus milk. Don't forget, that was 50 drops of milk. Get that right. Your third set of procedures will be ammonia plus milk, and that was only 25 drops of milk. I know some people made some errors, so if you accidentally used 50 here, what should you report? That you used 50. So that's what I recommended. Report what you did, even if you made an error. We don't want to change the science. Never. Good science. All right, now here comes the most important part. 4 and 5. 4. This is the data section. Does anybody remember what was the only thing we wrote here the last time? See attached forms. No, can't do that anymore. The data section is a pictorial reference of the data. Pictorial. Therefore, the only thing allowed in the data section are graphs, tables, and or charts. No sentences. Therefore, explicitly, no explanations. Where do those go? In the conclusion. Very good. That's the data section. And remember, I didn't teach any of this the last time. So you're going to have Roman numeral 4, period, space, and the word data. And then you must follow these rules or restrictions. So the next thing you will do, right under data, you're going to go letter A on a really nice margin or tab. We're going to get everything lined up this time so it's not ziggy-zaggy down the paper. You're going to write A. So Roman numeral 4 is here, A is there. and you're going to insert a graph. That means you have to know how to use Sheets and Google Docs together, or Excel and Word together. And you can create this. Now, if you don't know how to do graphs, tables, and charts in one of your word processing softwares, there's this new thing called the internet, YouTube. You're gonna have to learn, okay? Your graph should look like this, okay? I'm gonna put my graph, I'm inserting my graph. Here it goes, boom, boom. There's my graph. Now this first one is going to be a bar graph. Please do not write bar graph over here. I'm just telling you which one to pick. And it must be vertical, not horizontal. This axis will be labeled pH, and you will have it run from 0 to 14. Can you manage the run on any axis in a table using Google Docs or Word? Yeah, you can. So it shouldn't say 0 to 50, because what is the pH scale? 0 to 14, got it? Now over here, this one will be labeled samples. It'll be labeled samples. Then under each one of the samples, they will be labeled water, milk, lemon juice, and ammonia. Make sure you have all of these labels. Then your graph must have a super title, and it'll be included in the graph. This one will be called baselines. And everything but the A period, that will be part of the graph. And you can manage and change all of these things. You just have to learn how to do it. When you put it in, I would right-click format, bring it to the front so that you don't mess up any of your other formatting. You want it to lay on top of the document. Does everybody know what I'm talking about? A little bit? Okay. Now, you should have a bar graph. So this one should be about there, that one should be a little lower, and that one should be a little higher. And that will represent the pHs for the baseline sampling. That's what your graph should look like for letter A. Everybody with me so far? Okay, B. Then you got another graph. And you might have to work on your spacing or sizing of these graphs so they fit on the page and are visually pleasing. Should we have big gaps at the bottom of the page? No. If there's a big gap, resize things so that they're where they're supposed to be. B, you're going to have another graph. This one will be a line graph. Okay, caveat, with data points. Gotta have them. I'll show you what I'm talking about. Make sure you pick the right style of graph when you're inserting and managing these things. Now on this one, over here, we're gonna have pH running 0 to 14. This one here will be labeled number of drops. Super title will be milk plus lemon juice. Milk plus lemon juice. So the number of drops, that could run up to, I don't know, 12, 13, 14, whatever you guys did. Just manage it. Now for each drop, there was a pH recording, right? Right? Okay, so milk plus lemon juice, I should have a dot there. Whoops, let me go back to my pen. Dot there, dot there, dot there. Well, let me make them bigger, just so you can see them. Dot there, no, it should have flattened out a little bit. Now you record what you recorded though. Use your data. And then the line will go through those dots. Okay? Line graph with data points. You see how the dots have to be on the line. If they're not, I'm not grading it. They have to be on there. Now at one of these dots, something happened. The change occurred. You must indicate the change. Now here's one way you can do it. You could insert a drawing or a special character and use an arrow to point at that dot. Then you could insert a text box and you could type the word change in that text box. And then right click, eliminate the line. Then what I would do is select the whole graph, right click, and then group them together so now you have one image that you can move around. If you don't know how to do that, Figure it out. That's one way, inserting extra characters on top of your graph and then blending them together. Or, I don't know if you know this, you can double click on any one of these dots and manage that dot. You can make that dot bigger, smaller, you can change the color, and if you're using Word, you can actually insert special characters. Make sure you draw attention to the dot where what occurred. Did everybody hear that? If you don't, you will lose points on your graph because the data section is supposed to represent what you discovered. What do you think? Okay, now watch, I can save time. C is another line graph. Anybody anticipating where I'm going here? It's another line graph. You still have to have the data points. I'm not going to draw the whole thing because it's going to be exactly the same as this one, except it will be milk plus what? Ammonia. All of the labels will be the same except for that one, and you'll have a different line graph. Same rules show the change. Here's what I would do if I was you, especially if I was using Word and Excel. I would copy this one and insert it a second time. But now I have the same thing, right? Oh, that's easy. Once I insert the other one, I change the title, double click, open the Excel file, change the data, hit return, and I got a brand new one. You can do the second one in about 3 minutes. Just like that. 3 graphs, 1, 2, 3. Everybody got it? So C is a line graph like this one with different data and a different title. Everything else will be the same. That'll save you some time. But if you wanted to rebuild an original, knock yourself out, that wouldn't take very long either. Okay, any questions so far? All right, here we go. Oh no, oh no. Conclusion. Now at this point, you've done so much work, this is where you started writing things like, oh, I loved the musical. Cats was great. I would like to see it again and again. No. In the conclusion, you actually have to report what happened. But we need to do some instruction first. This is why I needed everybody else here. We need to do some instruction first. Okay? The main point of the lab was milk. Right? And then during the lab, you were adjusting what about the milk? pH. That's what you were doing. Now, if you didn't know this, milk actually represented life itself in the experiment. Because where did milk come from? Please get this right on the internet. Cows. Cows, yeah. That milk came from cows. Cows are living. So the milk has proteins manufactured by a living organism, and then you can affect those negatively with pH. That's what we were doing. But we need to know, what kind of milk was it? Oh, I never told you? Oh, I feel like the worst teacher ever on YouTube right now. Oh, no, that was skim milk. I intentionally bought skim milk. Okay, so now you know. Don't make faces. Those of you who like to drink the thick buttermilk, weird stuff. Skim milk has no what in it? There's no fat. Good. Jeez, I thought you guys didn't know that. There's no fat in skim milk. So nothing that happened was relative to fat. We took that out. We don't want to have any other factors. Okay. So now we need to talk about, if there's no fat in skim milk, what's actually in there? You guys tell me. Just so I know that American children know what's in milk. You can't even get one? It's a liquid made by mammals. Liquid made by mammals. We are 90% what?
Water.
Ah, there's one. Woo. I hope we don't get 1.2 million views. We may have just disappointed humanity. I don't know. Get his water in there, good. What else is in there? Remember, milk is what sustains baby cows and baby humans and all other baby mammals. It's kind of what we do. Oh, okay, there are minerals in there, that's true. There are minerals in there, but that's not going to affect the outcome of the pH. What? Which one? She said carbs. I would say sugar, not glucose. Oh, it's the one that some people can't drink milk because of it? It's lactose. So there is some sugar in there. I wouldn't say a lot. It's not like regular milk tastes like strawberry milk, right? Where does strawberry milk come from? Little strawberries. I'm just kidding. That's not true. What else is in there that a little baby cow would need? We took the fat out. That was important. But what else would a baby cow need? Nutrients, yes. What else would the baby cow need? What's that? And protein. Nice. Very good. And that was the focus of the lab right there. We will be talking in the conclusion about the proteins that are in the milk because that's what was affected by pH. Those proteins represent the proteins in any living organism that can be negatively affected by a change in pH. Now, of these proteins, watch. Milk is what we call supersaturated. Does anybody remember what that means from basic chemistry with Mr. Schellenberger? This is going on the internet. Somebody better get this right or I'm going to tell them to watch. Supersaturated. Okay, let's see if we can get this. If I have a glass of water and I'm adding sugar to the water, what will the sugar do in the water? It'll dissolve. Good, we knew that. What if I add too much sugar? Where will the extra be? It'll sink to the bottom. Will you be able to see it? It's supersaturated. That means there's too much sugar in the water and not enough water to do what to the sugar? Dissolve it. Did everybody get that? Supersaturated is when there's too much solute and the water doesn't have the capacity to form hydrogen bonds to dissolve it all. So there's extra. Hey, if skim milk is supersaturated, guess what there's extra of? I'm pointing at it on the board. Proteins, very good. You read that right in front of my finger. Protein. So watch. Some of the proteins are actually dissolved in the what? In the water. So if they're dissolved, you can't what? You can't see them. They're dissolved. That's how it works. But some of them are suspended in solution. They're in the milk, they're just not what? They're not dissolved. Wait a second. That means when you look at the milk, light is refracted back to your eye because it can't get through the milk because there's proteins holding it up. Hi. What do those suspended proteins create in terms of how the milk looks? Yeah, white or opaque, which means you can't see through the milk. You can't see through the milk because it's supersaturated with protein. There's a lot of protein in there, and that makes sense. Who needs all of those proteins in this milk from a mama cow? The baby cow, or in our case, humans. Yeah, we collect it and we use it too. So please keep this in mind. This is very, very important as part of your discussion. Now, the next thing I have to teach you is protein shape. All of the proteins in milk are what we call globular. Globular. Now, you guys should know from Mrs. Walzer's class that proteins are linear polymers. What's a polymer? A repeating sequence of similar subunits called monomers or residues. Very good. Somebody said that in the back. I don't think the camera heard you though. They're linear polymers. But proteins don't stay in a straight line. When you make a protein, you just take amino acids. I'm going to stand right here. Take amino acids, and then you connect it to a what? An amino acid, and then another one, another one, another one, another one, another one. But they don't stay straight. Because of the interactions between the amino acids, these linear polymers start to do three things. Does anybody remember from Mrs. Walzer's class? As you start to string them together, what do they do because of the interactions, positive and negative? Sometimes they repel, sometimes they attract. Sometimes they repel, sometimes they attract. People, it's BFT. Fold, twist. You don't remember that from Walter's class? There's no doubt she said that. They start to bend, fold, and twist. When they do that, our now linear protein takes on a new shape. It's a new shape. Now the shape of the proteins in milk are described as what? Globular. So I have to show you that and teach you how it works. Okay, ready? Watch this. Globular. These proteins are spherical. They're spherical. Hey, what's a sphere? It's a three-dimensional circle, like a ball. Everybody picturing it in your head? Okay, hold on. I think I have a ball. Where's that? No, I don't have it. No. Well, I can use this little baby one. Okay, that's a sphere right there. Oh, there you go. It's a ping pong ball. Now, if it's a sphere, it has a definite outside and a hollow inside. Everybody see what I'm talking about? Can you appreciate or imagine that there's actually space inside this ping pong ball? There's space in there. Definite outside, hollow inside. That is a globular protein because of the bend, fold, twist. Bend, fold, twist. Okay. So what I'm going to do is I'm going to draw this protein. I'm going to draw this protein. Now when I draw it, I'm going to cut this ping pong ball in half, and I'm only going to show you, I'm going to take the front off and show you the remainder so you can see the outside and the inside. Remember, it's one single strand, and then it bends, folds, and twists around on itself. Now it's not going to be a perfect sphere, but does everybody see that I'm kind of going in a circle there? Okay. Does anybody know from chemistry what keeps this line from unfolding? What is holding that shape together right now? What about chemistry is holding that together? Bonds, correct? Be specific. Waiting. Waiting. We're on YouTube. Waiting. What kind of bonds? No, not covalent bonds. No, it's not even a real bond. No, that's a real bond. No, can't do ionic. What? Hydrogen bonds. How do we represent those? Now I'm just going to add a few here. Hydrogen bonds are holding this linear protein together in this shape. I'm not going to write that because I already taught you that. Those are hydrogen bonds. Now we have a definite outside and a what? Hollow inside. Now we haven't done protein structure yet. So if you look at all of the amino acids that we use to build proteins, some of them are polar. What do they love? Water. And some of them are non-polar. What do they not love? Okay, good. So if this protein is sitting in milk, what's out here on the outside? Water is out here. So this thing bend, folds, and twists in such a manner that all of the polar amino acids point which way? Out. Yeah, Mac just said it. All of the polar amino acids are pointing out. They're all pointing out. Put a few on there. Where are all of the non-polar amino acids? They're pointing in. Because the non-polar ones, they love each other, but what do they hate? They hate water, so they're trying to stay away from it. Oops, that's not correct. I'll just add a few here. And when you hear the word globular, that's what globular proteins look like. Spherical proteins with polars outside, non-polars inside, and what's holding the shape together? What's maintaining the shape? Hydrogen bonds. Got it? Now we can talk about what happened. That's what you needed to know. You can always go back. I'll post this video. You can watch it 1,000 times. You only get credit for one view, though. So make sure you like and subscribe. And hit that notification bell in case I ever go live. You'll be notified right away. That's going on YouTube. Don't laugh. It's going to be a good show someday. Hey, paragraph 1. We need to talk about what happened when you took milk and you added lemon juice. Now remember, you need a data point and then an explanation. No extra weird fluff. No. Science is direct, boring, and to the point. Ooh, that hurt my ear a little bit. That was so good. Now, I'm not going to put it in paragraph form. I'm going to do bullet points, and then you'll write the paragraph. Okay? Bullet point. We need a data point. At, drop, whatever drop it was. At, drop, question, when adding lemon juice, at, drop, question mark, when adding lemon juice, wow, that looks bad, there we go. Something happened. There was a change. You must start your first sentence with that. Nothing weird, no lead-in sentences, no teasers. We're not writing a short story. You just started out with paragraph 1. At drop, whatever drop it was, when adding lemon juice, there was a change. Second sentence, you have to identify what the change was. What happened to your milk at that drop? It curdled. You could also say that it got chunky. Now you've defined what happened specifically. What do you have to do the rest of the way? You got to explain it. Okay? Why did the milk get chunky when adding lemon juice? Okay. Lemon juice is what on the pH scale? Not a number, just tell me what it is. It's an acid. Okay. So if you're adding acid to the milk, what are you technically adding? It's an acid. I already taught you this. What do acids add to solution? Protons. Yeah. Little H pluses. Ooh. As you add lemon juice, the number of protons is going up, right? When you put them in there, the protons act like, this is my terminology, this is not science, missiles. Because how are protons moving in solution? At high rates of speed, right? They go everywhere. Mm-hmm. Those protons disrupt hydrogen bonds. Whoa. Whoa. They disrupt the hydrogen bonds. What? I'm going to go back right there. I'm going to put a proton right here. And I'm going to put his motion in red. Hey, can that proton just fly right through that protein? Yeah. Yeah. Vroom. And when it does, it disrupts what? Uh-huh. What? Going back to black. Wait a second. Those hydrogen bonds are maintaining what about that protein? Not the structure. The amino acids are the structure. It's shape. Anybody see where I'm going here? Those hydrogen bonds are maintaining the shape. If I break them by using protons from an acid, from lemon juice, look in the camera, everybody. What's going to happen to my protein if I start breaking hydrogen bonds? It will unravel. That protein is going to unravel. It can't maintain that three-dimensional spherical shape without the hydrogen bonds. So if I keep breaking them, it'll start going bing, 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 and it'll unravel. There's a name for that. In proteins, that's called denaturing. Might want to include that. You will say they unraveled, and then you will tell me what that word is, denaturing. Wait a second. If I unravel that protein, what's going to get exposed? The nonpolars. Watch this. As a result, the nonpolar amino acids are exposed to what? to the water. Oh, no, 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 no. They were in there hiding. Can somebody tell me what happens when you put non-polar and polar together? They repel or separate based on? So when the non-polar portions or amino acids of that protein are exposed to the water, because you used acid to crack this egg open, those proteins fall out of solution. Anybody know what that's called in chemistry? Yep. I heard somebody say it. Creating precipitate or precipitation. Then the proteins clump. These milk proteins start to clump together because non-polar likes non-polar, polar likes polar. They start to stick together. Huh! That creates chunks. And that's officially when your milk did what? It curdled. And you officially killed the milk. Can you ever make it look like milk again? No, you just made cheese. You made cheese. So if you add too much acid to a living organism or a living cell, will it survive? Nope. Where do we like to be? Where do humans like to be? 7.4. That was just paragraph 1. How am I doing on time? Terrible. That is everything you need in paragraph 1. Notice that it's in order. How should you present it in your paragraph? In order. In order. Paragraph 2. This time you're going to do milk. Whoops, oh no. Plus ammonia. Milk plus ammonia. Now this one I'm going to go a little bit faster to see if you guys can put this together. Okay? Milk plus ammonia. You need a data point first. Okay? When adding ammonia to milk, at drop, you tell me, there was a what? Ta-da! Then you must tell me what the change was. What happened to your milk in this portion of the experiment? Aha! It became translucent, or at least clear or clearer. I'll take either one of those or both. Then you need to explain why. You were adding what? A base. You were adding a base. Now I forgot one little thing, so I'm gonna jump back here real quick. In milk plus lemon juice, you want to talk about dissolved proteins. Make sure you talk about the dissolved proteins. Everything that happened to them. Sorry about the jump back. My next note was gonna lead me into, All right, I'm gonna finish this up. There's no crowd, but here's where we left off, okay? At drop, whatever, there was a change. The change is it was translucent, or it got clear or clearer. And the reason, now we have to explain it, because you're adding a base. What were you adding? Whoops, I knew that was gonna happen. What were you adding? You were adding ammonia. Ammonia is a base. Now in this case, you were affecting the suspended proteins. These are the ones that are not in solution. In the last paragraph, you were affecting the dissolved proteins. Now you're doing the suspended ones. These are the ones that are making the milk white. Now here's the cool part, okay? You actually have a protein like this. All of the polars are on the outside. I'm not going to draw the whole thing because you already know what this looks like. Non-polars on the inside. Now, because they're suspended, they're not in solution. They're just hanging in the milk. Well, wait a second. Let's introduce ammonia. You guys know from previous instruction that ammonia is a polar molecule, so it's partially charged. This end is partially positive, this end is partially positive, that end is partially positive, and because the electrons spend most of their time up here, it's partially negative. So when you put ammonia in the milk and these suspended proteins are there, they're now vulnerable. So if that amino acid is partially positive and that end of the ammonia is partially negative, watch what happens. What forms between the suspended proteins and the additional ammonia? Oh, I know, hydrogen bonds. Hydrogen bonds form. So now technically, you guys remember, I'll come back to this word. Hydrogen bonds, when they form, cause solutes to dissolve. What? So the suspended proteins that were in the milk are now getting dissolved into what? Into the ammonia. The ammonia is pulling, through hydrogen bonding, the suspended proteins into solution with the ammonia, not the milk. So wait a second. When something dissolves in water, you can't see it anymore. When something dissolves in ammonia, you can't see it anymore. Huh. So as you increase the amount of ammonia, the suspended proteins are dissolving. Whoa. Those suspended proteins were the ones that were causing the milk to be opaque. If they're not there anymore, if you can't see them anymore, then the milk gets clearer. What? The milk gets clearer. Now, how does that affect real life? If you had functional proteins in cells, and they were getting dissolved and pulling out of solution, the cell wouldn't have access to those proteins wouldn't function, and potentially, what could you do to a living cell just like you did to the milk? You could kill it. pH is very important. What's our pH? This is human pH. Life likes to be around 7. If you go up the ladder, bases will cause issue. If you go down the ladder, acids will cause issues. In fact, if you go too far, it'll cause death. And how about with that, we end this video. If you have any questions, let me know.